What we're actually going to spend most of this chapter talking about, though, are molecules and the bonds inside of molecules, which are covalent bonds. So remember, there are ionic compounds and molecular compounds. Ionic compounds are usually made out of what? Metal, nonmetal. Okay? Metal, nonmetal. And we have metal mixed plus, nonmetal mixed minus. They attract. Okay? Molecules are different. Molecules are atoms that are bonded together in a specific group, and molecules contain only what? What kind of elements are in molecules? Non-metals only. You better put a big star by that or something, because that's how you know if something is a molecule. It's made of non-metals only. So with non-metals only, we have to do something different, because we can't transfer electrons, because non-metals just like to gain electrons, right? Non-metals are only just like 1 or 2 or 3 electrons short of being a noble gas. So they all want to gain electrons. None of them are going to just give electrons away to make an ionic bond. If they all are just kind of grabby and want electrons, then a different kind of bonding happens. So let's look at the simplest molecule, an H2 molecule. Let's start with 2 H atoms. That's an H atom. That's another H atom. Okay. Are those individual H atoms stable, just like that? No. Why not? Yeah, their box would be half full. They would only have 1 electron. How many electrons would they like to have? They would like to have 2, because that's what helium has. Okay? Helium is 1s2. These are both just 1s1. We got a half full orbital, which is not too happy. Okay? They both want another electron. Okay? And it's not going to be the case where one of them is just going to say, here, you can take that, because that one wants an electron too. So instead of just giving and taking, we've got like 2 children that both want toys, so they're going to share. Okay? And if they're good children, that's what they would do. We'll talk next time about what happens if they're bad children. But if if they share, what we end up with is something like this, where if they get close enough, now they both see their own electron, but they also have access to the electron from the other atom. Okay? And those 2 electrons will live just right in between those atoms. Okay? What we formed right here is a covalent bond. That is a pair of shared valence electrons. And we actually draw covalent bonds as a line. But we have to remember, when we draw a line that's attaching 2 atoms like that, it's 2 electrons inside of there. Those 2 electrons are held into place, right? They're held in place there because they're attracted to the nuclei of both of those hydrogen. Okay? What's inside of a hydrogen nucleus? What's inside of a hydrogen nucleus? 1 proton, and that's it. Okay? And protons have what charge? Positive. Okay? So we've got a pair of electrons that are going to be attracted to the proton in there and the proton in there, so they sort of get held in place right in between those atoms. And there's an optimal distance where they get held in place, where they're attracting but not repelling. Okay? So we end up with this stable covalent bond that ends up holding those 2 atoms together, okay? because of that attraction. And now those atoms are both stable because we have those 2 electrons in there that each of those nuclei can sort of see. It's sort of like, right, that 2 electrons in here is sort of like 1s2, which is stable. Okay? It's not quite the same as 1s2, but it's similar enough so that it's stable. And that's how we formed a molecule. So can you see how molecular compounds are very, very different from ionic compounds? Okay? We've talked about how they're different when you're naming them, right? But here is how they're very different in their structure. Ionic compounds are made out of alternate charge ions that are just all stacked up and just all attracted to their neighbors in every direction. Molecules are very particular groups of atoms that are bonded together by sharing their electrons. And that can only happen in very specific ways. So that's why we don't have like another H out here or something like that. We have just this pair of atoms because that's what we've needed to fulfill the desire of those atoms to become stable. Okay? So let's make a little bigger molecule. Remember, this only happens with valence electrons, though. The inner electrons are already stable, so they're fine. Okay? So how many valence electrons does carbon have? Carbon has 4 valence electrons. Okay. Oops, wrong page. Carbon has 4 valence electrons. H has 1 valence electron. How many valence electrons would carbon like to have? Carbon would like to have 8, like neon. And the reason carbon does not form a -4 charge is because it's really very difficult for it to rip 4 electrons off of something. But it can get 8 electrons not by just taking electrons, but by sharing electrons with another nonmetal. Okay? That's how carbon becomes stable. And that's how all these nonmetals become stable when they're bonding with other nonmetals. So what we end up with is a structure that looks like this. And I'm going to draw it with a shape that will look familiar to you once you have done the lab for this week. I'm going to make that one go straight up. Okay? That carbon started with 4 valence electrons. Each of those hydrogens had 1 valence electron, and by forming covalent bonds, remember how many electrons are in this line right here? 2. Okay? So by hydrogen bringing in 1 electron and pairing with one of carbon's electrons, now how many valence electrons does that carbon have access to around it? Yeah, this carbon now has access and that makes it stable. Okay? So 8 valence electrons tends to kind of be the key to stability. And we saw why that is with the structure earlier on. 8 valence electrons is 2 in an S, okay, that's filled, and then 6 in P's that are filled, and you end up with this shell that's nice and symmetrical and totally full. Okay? So let's complete this little table here to help get that idea across. Noble gases, except helium, but all the other noble gases have how many valence electrons? 8. Because it's S2 and P6, essentially. Okay? Stable main group ions have how many valence electrons? 8 again. A regular O would have 6, but O2 minus would have 8. Okay? Sodium would have 1. Na plus, you remove that 1, and it's sort of like 0, but then you'd actually be counting the 8 valence electrons from the row before it. So it still has 8 valence electrons. Okay? So any stable main group ion has 8 valence electrons, and covalently bonded atoms, like this carbon here, have access to 8 valence electrons. That's the octet rule. That atoms want to have 8 valence electrons in order to be stable. We saw a picture from the orbital diagrams why that's important. It's essentially because of symmetry. Okay? It makes them symmetrical. But that's going to be our sort of guide in making atoms stable. What do we need to do for it to have access to 8 valence electrons? Okay? So those of you that did lab this morning, you might have to help us out a little bit. But those of you that will be doing lab on Tuesday, this will be very useful information. I would actually recommend, so you'll be watching the video, I would actually also recommend before you come to lab filling out the page of pre-lab questions. There will be a table that looks something like this, but the questions in that will help you quite a bit in the experiment. Right? So let's do H, C, N, O, and F. Okay? Number of valence electrons. This won't be too hard. Right? H is just 1. How many does carbon have? Yeah, valence electrons. 4. N has 5. O has. F has 7. Okay? Number of valence electrons. That's just if you number 1 through 8 across the main group. Okay? That's all that is. The number of covalent bonds, let's leave that blank for a second because we can make sort of another row down here that says stable number of valence electrons. Okay? And hydrogen is going to be different from the other ones. How many valence electrons would hydrogen like to have in order to be stable? Hydrogen would like to have 2. All of these other ones, though, they would like to have how many? That's what we just got done saying. That's the octet rule. Sometimes the fact that hydrogen wants 2, sometimes that's called the duet rule. Okay? But the octet rule, everything except hydrogen and helium would like to have 8 valence electrons to be stable. Okay? So when we're looking at number of covalent bonds that an atom forms, we have to remember that each covalent bond we've formed has given that atom access to an additional electron. Okay? We started out like this. Okay? If you look just at this blue one here, by pairing up, it started with just 1 electron. Now it has access to 2 electrons. Okay? Carbon, if you want to draw it like this, carbon started out with 4 valence electrons, and by pairing up with those hydrogens, it now has access to 8. Okay? So, how many covalent bonds did that carbon make? It made 4 covalent bonds. Okay? There are 4 pairs of shared electrons. And it made 4 because each of these hydrogens that came in gave that carbon access to 1 additional electron. Okay? So hydrogen. So how many covalent bonds did H make? Just 1. How many covalent bonds did carbon make? 4. Okay? If nitrogen starts out with 5 and wants 8, how many additional electrons does it need to bring in? It needs to bring in 3, and each time we make a covalent bond, we're bringing in 1 additional electron for it to have access with. Okay? It pairs up one of its existing with one of the new ones. So it's going to make how many covalent bonds? 3. And O is going to make 2, and F is going to make 1. Okay? So it's a really simple pattern that forms, but the reason for it is that by sharing electrons, we can get to 8. By pairing up one of its existing electrons with an electron from another atom, we make a covalent bond that gives it access to 1 additional electron that it didn't see before. Okay? So this is going to be very useful for us, especially this one right here, because this will allow us to predict how many bonds a particular atom will make in a compound. Remember I said there are very specific ways that covalent bonds can form. Okay? It's not just everything just all over the place. It has to be very specific because we have to combine existing electrons with the paired up electrons for them to become stable. So what you're going to get practice doing in lab on Tuesday morning, or what you had practice with today, was drawing a proper Lewis structure for a molecule. And what we have to do in a molecule to draw the proper structure And what you're going to need to practice, because anybody can just draw atoms and connect them together and make some dots and whatever. What you need to practice doing is looking at these three criteria here to make sure that you've drawn a valid structure and not just a nonsense structure, right? So a valid structure, or a proper structure, will show all of the molecules' valence electrons, okay, either as lines for covalent bonds, as dots for electrons that are unshared. Okay? There can be valence electrons that just remain on an atom and aren't shared. Okay? But all of them have to be accounted for. All atoms have full octets or duets. What that means is that each atom is stable. Each atom will have 8 electrons around it, whether it's as bonds or unshared electrons. What do duets apply to? Hydrogen, yeah, pretty much hydrogen. Okay? And then each atom has the correct number of bonds. Okay? We did that here. Atoms will typically only form the number of bonds they need in order to gain a octet. There are going to be some exceptions to that, which we'll maybe talk about next time if we get a chance. But for the most part, small, simple molecules, carbon will have 4 bonds, O will have 2 bonds. Okay? And that's one you have to really be careful about, because you could have the right total, you could have full octets, but it could be a structure that is not a good structure, not the actual way that the atoms are bonded, because oxygen will typically just make 2 bonds, and that's pretty much what it needs. Okay, so instead of drawing these ones out right now, I want to give at least the Tuesday morning class a chance to do the lab and work on these. If you already did the lab this morning, you could try these without the aid of your model kit. One nice thing is, in the lab, we get a model kit that has the right number of holes that automatically tells you how many bonds each particular atom will form. So if you've filled up the holes, you've got them connected, right? Okay? So without the help of a model kit, though, you need to rely on this idea right here. Okay? The idea that carbon makes 4, N makes 3, O makes 2, F makes 1. Okay? You're going to have to be able to know that. So you can write out that little table or do whatever you need to make sure that works. Okay? So yeah. So we'll practice again in class next time. We'll practice drawing these and make sure that we're all on the right shape. What I do want to do just before we leave is start thinking about the shapes of molecules. Because it actually turns out that by drawing the structure and just by looking at sort of where the atoms are, we can start to think about what those angles will be for the bonds in there. Okay? So let me draw you just a couple of simple structures here. I'm going to draw you the structure of CO2. Those of you that did lab this morning know that it has to look like that. Can somebody from lab this morning tell us why I made 2 double bonds there instead of just 2 single bonds? What does carbon need to make? Carbon needs to make 4 bonds. Okay? In other words, from our little note here, carbon needs to make 4 covalent bonds. But if I only have 2 atoms to attach to, then we have to bond those O's twice, it turns out. Okay? So somebody else from this morning, tell me what else I need on this. Dots on the O's, because I'm going to put 4 dots on that O there, because why? Because this O needs to have 8 electrons around it to be stable. It's got 4 electrons that it sees in those bonds, so now it's going to need 4 dots on it, just electrons that are unshared. So now looking around that O, it has 2, 4, 6, 8. It has its octet, and it's full. Would this carbon have any dots? No, because if we count those electrons, 2, 4, 6, 8, it already is full. It has 8. Okay? So we'll do the same thing over here. Okay? I'm going to draw CO2 that way, but down here, H2O, I'm going to draw it bent. Okay? Somebody, what else do I need in this structure of water? Dots? How many? The octet rule says that every atom needs 8 electrons to be stable. Okay? So, how many electrons would I need on that O for it to have 8? I would need 4, because remember, each of these lines is a pair. That's a pair. There's 2 in there, and there's 2 in there. So then I need 8 like that. Okay? You can almost see where oxygen's 6 original valence electrons were, because it would have had these 4, and it would have had 1 electron in each of those bonds. Okay? That's where oxygen's 6 original valence electrons came from. Okay? And 1 paired with a hydrogen to make that, another one paired with that hydrogen to make that. Okay? So, any idea? Both of these, CO2 and H2O, both of those have a central atom and 2 atoms attached to the central atom, right? Any ideas why CO2 is linear, the atoms are all in a straight line, and H2O is bent? What's the difference, especially on the central atom? What's the difference? And you can actually, and it's not the double bonds. It wouldn't, you might think so, but it's not the double bonds. What is it? Take a look at the definitions there. What's the difference? 2 atoms attached to the central atom. What do I mean when I say, any idea what lone pairs are? A lone pair is a pair of unshared electrons. Okay? Those are the dots that we draw in these structures. Okay? And I think one of the total keys to understanding the shape of molecules and the angle of these bonds is that if our central atom has dots on it, if our central atom has unshared electrons, those dots take up the same space that a bond would. Okay? So we're here, there are dots out here, but those don't take up space on the central atom. This carbon is just attached to the O there and the O there. The only things on that carbon is this bond to this O and the bond to that O. So they spread themselves out as far as they can from each other because their electrons sort of repel. But this O has a bond to an H, a bond to an H, a lone pair, and another lone pair. So those lone pairs on that central atom take up space, and they actually squeeze these bonds down towards each other. Okay? So the main idea here is that if our central atom has lone pairs on it, it will take bonds, which were normally just spread out, and push them towards each other. Okay? So I think that's where we're going to end today. Next time we're going to do a little practice actually drawing these structures, because at least more of you will have had the lab, and then we'll continue on talking about shapes.